Earlier we used the coefficient of variation to compare the returns distributions of two portfolios. We had the expected return, but we also had the standard deviation of returns. So that when a portfolio has a higher expected return than another, but also has more risk, how do we compare them? Well, this alternative way to compare them is based on the shortfall risk, or the probability that a portfolio return, or we can do it in a monetary value, will be below some target return or target value. And so the measure that's been used is Roy's safety first ratio. Now what Roy's ratio measures is the number of standard deviations that some target return is below the expected return. So this safety first ratio, we've got the expected return minus the target return. That target could be 0, could be the risk-free rate, could be any number. As long as it's less than the expected return, we'll get a positive safety first ratio here. So let's take a look at how this might work. We've got portfolio A and portfolio B, and as is our usual story, we've got an expected return that is higher for portfolio B, but it also has significantly more risk. Its standard deviation returns is 20% as opposed to 12% for portfolio A. And then we've got portfolio C. Its expected return is lower, but it's also got the lowest risk here. So now we need to rank these portfolios, and what we're going to rank them on is their shortfall risk, their probability of generating a return less than 3%. So what we're looking at here with our safety first ratio here is how many standard deviations, if we look at this here, this tells us how many standard deviations below the mean is our target return. So here's our target return of 3. Here's our expected return of 9%. We're saying, well, our target or threshold return is half a standard deviation below the mean. And so we can translate that into a probability. And so if we look at the probability of being more than 0.5 standard deviations below the mean, maybe I'll just draw it out here if we have some sort of normal distribution. So here's our mean return of 9%. Here's our target return of 3%. So now we're saying, well, our shortfall risk is the probability of a return less than 3%, and we're saying in standard deviations, this is 0.5. Standard deviations, 0.5, standard deviations below the mean. So that's what we're reading off right here. Portfolio B, we do that same calculation, and we see that our threshold return of 3 is 0.4 standard deviations below the mean, and for portfolio C, 0.44. So which do we like? Which is going to give us the lowest shortfall risk? Well, the further below the mean is our threshold return, the smaller the percentage probability in the tail. So we like the larger safety first ratio. And we can see that if we looked at the standard normal probability tables and say, well, what's the probability of being more than 0.5 standard deviations below the mean? 30.85%. And each of these has a higher shortfall risk, portfolio B and C, a greater probability of falling short of 3%. So that's the idea of Roy's safety first ratio. And just note that even though we're talking about 0.5 standard deviations below the mean, in Roy's safety first ratio, it's a positive number. So don't let that confuse you. A log normal distribution, as we look at common probability distributions some more. Well, we use a log normal distribution, and really I think all you need to know about it is maybe just one thing, maybe two things, okay? The first thing is it can't take on any negative value. It's bounded from below by 0. So if we're modeling prices of assets, well, price can only go to zero. So if we use a normal distribution, which actually can go from minus infinity to positive infinity, that's not ideal for modeling asset prices. So we often use a log normal return. Well, where does a log normal return come from? Well, this mathematical e to the x is where we get it. So if x is normal and we translate every outcome into e to the x, then we get a log normal distribution bounded by 0 on the lower side. And so that's all I think you really need to understand for the limited amount of use we'll get out of the log normal distribution. So best for modeling prices or price relatives, 1 plus the percentage change. So if the percentage change in a variable, if it goes to 0, that's minus 100%. So this price relative, 1 minus the return, goes to 0. So that's what I'm saying. We can model those with a log normal distribution. And the other side of e to the x, I'll tell you one thing here. If we took e to the x and then we take the natural logarithm of that, it gives us back x. So the logarithm and e to the x are kind of two different sides of the same operation here. So now we're going to turn our attention to continuous compounding. You remember when we were looking at compounding periods and we said, well, the more frequent the compounding, the higher the effective annual yield or effective annual return. So we start out, we said, well, with annual compounding, we get our stated rate back. With semi-annual compounding, our effective rate's a little higher. Monthly compounding, a little higher. Daily compounding, a little higher for a given stated rate. Well, the limit of that is continuous compounding. As we let those compounding periods get shorter and shorter, or the number of compounding periods get greater and greater, our limit is continuous compounding. And so the learning outcome here wants us to know how to get the stated rate of return that on a continuously compounded basis would give us a holding period return. So here we've got a 1-year holding period return, and as you recall, a holding period return is an effective return. It's actually, if you started with $100, you'd have $120 if your holding period return is 20%. And we want to find out, well, what would be the stated rate with continuous compounding that would give us an effective annual rate of 20%? So that's what we're up to here. And this is just 1 plus the percentage return, okay, 1 plus our percentage holding period return. And we're just going to take the natural logarithm to that. You can find it on your calculator. See that it's the natural log, and the section function of that is the e to the x function that we used for our log normal distribution. And so with a stated rate of 18.23%, we would get a holding period return of 20%, going back the other way. But the learning outcome statement really requires us to put in a holding period return and get the stated rate with continuous compounding. Here we can see, going back the other way, our ending value over beginning value, okay, that's just 1.2, 1 plus 20%. Okay, that's what we just figured out. And going back the other way, as I said, your e to the x function, if we put in the stated rate, we get the effective rate. Let's talk a little bit about simulation. Say we've got a situation where we really don't know what the distribution of price outcomes is. This could come up with options, for example. We've got options, and there's a lot of inputs that go into it. The risk-free rate goes into that. Assumptions about how volatile the price of the underlying asset is. And so what we could do in Monte Carlo simulation is we take each of those risk variables and specify a distribution for that. So we'll say, okay, interest rates, here's our distribution of interest rates. And prices of the underlying asset, here's our distribution there. Maybe use a log-normal distribution so it's bounded by 0. And so for all our variables of interest, they go into the determination of an options price at any point in time. We just we tell the computer, well, pick a price from this distribution. Pick an interest rate from this other distribution. Pick a volatility from this, expected volatility from this other distribution. And then use those to calculate the options value. Okay. So we price the derivative using these values chosen from our specified distribution for each variable of interest or each risk variable that's involved. And then do that thousands, do it 10,000 times. Well, now we've got 10,000 different prices. What are we going to do with those? Well, we can say, okay, what's the mean? What's the variance? And now we've got a description of the mean and variance of the price of the option. So that's Monte Carlo simulation. Now, a couple of caveats. We've got to specify the distributions, right? So if it's a log normal, we've got to specify, well, what's the mean? What's the variance of that? So it's the same old thing with computers, garbage in, garbage out. But if we could specify these pretty closely, we could get good information about the distribution of this options price, which we couldn't really figure out the probabilities for without doing this computer-intensive simulation. Now, an alternative to that is historical simulation. So it's similar to Monte Carlo, but we're going to look at historical data. So for the stock price, for the stock underlying this option we're trying to develop the probability model for. And so we just go back to historical stock price and say, okay, choose one at random. Go back to the expected volatility or the interest rate. Well, go back and pick an interest rate. So that's historical simulation. So the advantage is we didn't have to estimate the distribution of any of these risk factors. We didn't have to estimate the stock price distribution for the underlying stock. We just picked values from its historical data. So that's the advantage. The disadvantage is that future outcomes for risk factors may be outside the historical range. So if we think back to the mortgage crisis, they were looking at the expectations for the performance of mortgage securities using historical simulation. And looking back, well, as we moved forward, some of those distributions just clearly changed. And the future wasn't like the past, so historical simulation gave us some pretty bad answers in that case. So that's the disadvantage. If future outcomes for the risk factors are outside the historical range, then there can be trouble using this historical simulation.